So with the last clip, we're essentially done with the chapter, but I wanted to talk a bit more about the implications of the spectral theorem so that you see kind of why it's neat and what it really implies, and also where it gets the dang name from, right? So that I don't know if Axler even talks about this, but the spectrum of an operator is the list of eigenvalues. So it's denoted by a sigma, just the Greek S for spectrum, sigma, whatever. You know, mathematicians are not super original when it comes to notation. So the spectrum is just the list of the eigenvalues. And it's very important that you have the multiplicity right. So if, you know, 1 is an eigenvalue of multiplicity 3, then you need to have 1, 1, 1 appearing in that list in some order. The order's not super important, but for practical applications, and we'll talk about one of these later on, it's quite often good to take the biggest one in absolute value first. And so it might be that there's a couple of different ones with the same absolute value, whatever, doesn't matter. You can always order them in non-decreasing order like this. Sorry, non-increasing order like this. Okay, and then one other piece of notation we're going to need is I'm going to take p lambda here just to be the projection to the eigenspace of lambda, the lambda eigenspace of t, that is. Okay, so if t is self-adjoint, by the way, that definition up there for spectrum, that's for any operator. It doesn't need to be a self-adjoint operator. Any operator you can talk about its spectrum. So if t is self-adjoint, then let E1 through En be the corresponding eigenbasis, orthonormal, let's see, be the orthonormal basis of eigenvectors of t. Okay, so then if I do t applied to the vector v, then I can expand that vector in terms of the eigenbasis, and using inner products, it's going to be v e1 up through v en. And then I can use linearity. So then, let's see, so each of these is a scalar, so it can come out front. So we have VE1 TE1 up through VEN TEN. All right, and so now, so this is by the fact that t is linear. And then for the next trick, let's say, so these guys are all eigenvectors of t. So t times E1 is going to give us lambda 1. And t times En is going to give us lambda n. Okay, well, so that was maybe a terrible thing to write. How about TEJ equals lambda JEJ? There we go, much better. And then, so what do we have here? So now let's look at what's going on with an expression of the form V EJ EJ, right? So if we have, say here's our vector v, and then we have our orthonormal basis, there we go. So here's E1 and E2, then this part here is VE1 E1, or in other words, it's the projection to lambda 1 of v, that is the lambda 1 eigenspace, right? So that's how we're doing this decomposition. So if we go back to what we have over here, this is lambda 1 times the projection to the lambda 1 eigenspace of v. And these are all summed up. Oops, that's lambda n. And the reason why I like doing that is because then I can factor out the n again. The v, rather, sorry. And so that gets us that what we have out here in front. So this is the sum over all the lambdas in the spectrum of T of lambda p lambda applied to V. And then that tells us that that's exactly what T is. So this is the spectral representation of T. It's a sum over the spectrum of lambda times projection to the lambdath eigenspace. And this also works for infinite dimensional V. And as you might guess, it's a bit of a longer story with some more technicalities and a bunch of junk having to do with checking limits and so on and so forth. But it can be done. And so in that case, T looks like an integral over the spectrum of T of lambda d p lambda. And so making precise sense out of like, what is this widget right here? It turns out this is what's called a projection valued measure, but that's beyond the scope of this course. We don't really need that for right now. I just wanted to give you a pointer that this theory goes, quote unquote, all the way up. So that's the spectral representation of an operator.